Okay, so welcome to this last tutorial 6, that we are going to talk about computational modeling. So first of all, we want to say that these slides that we are going to present here are a summary of the information that we have included in the PDF that you can find in the web page. That is more extensive, and all the information that we give there has more information than the one that we will give here. And also that we are going to present these slides also in combination with the MATLAB scripts that you can also find in the GitHub. And also Seb will give you the instructions to how to run or how to go to these scripts in the virtual machine. So I think that in Slack he will write them. Okay. So we are going to start this tutorial saying that here we are going to talk about the computational modeling that, well, it is a recent tool that has been proposed to understand the collective behavior of the dynamics. So the main idea of these computational models is to idealize the processes that are the responsible to generate the behaviors of the observable spatiotemporal features that we can find in the both signals or in the signals that we have. And the idea of these computational models is that we are going to have some brain regions that can be modeled. So the dynamics of these brain regions will be modeled, and we are going to consider that these brain regions are interconnected among them. So furthermore, these computational models allow us to study the non-trivial interplay between the function and the structure. So for that, these models, as I said before, we can extract information about the relevant observable features that we can observe in the combination with of the function and the structure, and also give us an interpretation of the model parameters that can be related with, for example, with the biological aspects of the brain signals and brain structure. So in particular, in this tutorial, we are going to talk about the whole brain model that is based on coupled oscillators that are describing oscillation close to a Hopf bifurcation. So for that, we can say that we have some Hopf oscillators. So in this model, what we do is we have the functional connectivity. So we have the fMRI data and the dynamics of the brain signals, there. And we are going to consider that the brain regions that are working with some dynamics are interconnected among them using the structural connectivity. So we will have some interactions between the regions. And if we consider that the local dynamics can be described by a Hopf normal form, we can simulate the dynamics that we see. The network and local dynamics that we see in the signals. So this Hopf oscillator has the key point, or the key importance, that it has a bifurcation parameter that considering the different this bifurcation parameter can describe different dynamical regions. For example, if we have a negative bifurcation parameter, we have noise. When we have a positive one, a positive bifurcation parameter, we have oscillator, and in the middle we have the phase transition between both. This is a mesoscopic model of the brain. Later we will give more detailed information about this model. And another important aspect of this model that we are going to work with in this tutorial is that it has been successfully applied to simulate the nonlinear dynamics of different brain states, such as during the resting state or in different brain states, and that also explain the brain mechanisms using the parameter and the changes in the parameters. Also, we can explain some features of the brain mechanism and how it changes in different brain states. So now Manel will explain with more details the description of this model.
Yes, thank you, Anna. can you mute yourself? Thank you. So Manel has described that in this sort of model, we combine structural connectivity with functional connectivity that we assess with real empirical signals. So let's go to the description, the equations that describe the model. So here we're going to dissect the model. We are going to assess and evaluate the different parameters that we have in it. So imagine that we have, for instance, brain signals parcellated in 84 regions, as we will see later. We would have 84 equations. Each Z is describing the dynamics of each single region. And then what we have here is initially in this part here, we have recurrent activity. So we have one parameter, which is called the bifurcation parameter, which controls for the local dynamics of each single node. We have the local frequency, which is what we would say the dominant frequency in the spectrum of the signal. Then we have a second part here, which takes into account the connectivity and the influence from the other nodes. So we have, for specific node J, we have the contribution of all other nodes going from K1 to N, which is controlled by the structural connectivity. So this is where the structural connectivity comes into play. And then we have a global coupling parameter that scales all these factors here. And in addition, we have some Gaussian noise. So from here, you have to take into account that, as I said, the second part here controls the influence from other nodes into each region, into each node in this network. So in order to divide or study what is the contribution of the different terms that we have in this equation, for the first part of the tutorial, what we do is forget about the influence of other nodes. So we just take one node and we will study the local dynamics. So we go now we will go now to part 2, understanding just one Hopf oscillator. So now we take, this is basically the same equation that we had before, but we have removed the contribution from other nodes. So we have only one node. And this single node is described by Z, which is a complex valued state variable. And this complex valued state variable, if you take the real part, as you will see in the scripts when we run the MATLAB, the real part is the signal that we actually measure. And the imaginary part of Z is instrumental just for the equations, just for us to build the dynamical model. Then here we have the Gaussian noise, which is like introducing a very small perturbation at each single time point. And then we have the intrinsic frequency and the bifurcation parameter. So we are now interested in studying what this free parameter that we can control, what this free parameter does on the local dynamics. So this bifurcation parameter controls for a specific type of bifurcation, which is called Hopf bifurcation. So if we have an A which is positive, we have a stable limit cycle, and then we will end up having oscillations. If A is negative, then there is no limit cycle. So we just have a fixed point at 0, 0, and therefore we only have the contribution from noise. So every time there is an input into this region, this will end up damping, and we will end up just with noise. In the other case, any perturbation will end up in a sustained oscillation. So this is the key concept for this first part. Now, this bifurcation parameter, we can usually summarize this characterization that I just described with such a plot in which we see that here we have just one state, and we end up having two different, so just one state in which we have an oscillatory regime. So in this exercise, we will work with a Hopf oscillator. You can now start opening your virtual machine and opening exercise 1 in MATLAB. What we will do here is to plot the dynamics of the Hopf oscillator for different values of the bifurcation parameter, A0, A positive, and A negative, and understand what is going on when we change this parameter.
Okay. So here we have the script of the first exercise. This script contains 3 main parts. In the first part, as you can see here, we are going to define the basic parameters. So for that, first of all, we set the the frequency of each node to 0.5. This is the internal frequency of the oscillator. And we are going to set also the connectivity between the oscillator, that in this case we are only going to have one, so there is no connectivity, it's all 0. And here as default we have 0, which would be we are going to have this oscillator in the phase transition. So these are also the basic parameters of the models. Here we defined it's only to define, for example, the time step and other model parameters. And here we have the actual model. As you can see here, this in the line 50, this will be the equation of the model, the equation that Manel has explained. So in this case, we have here the local bifurcation parameter, so the A, that in this case we have set to 0, we have the omega, and we have the different terms of the equation, as you can see here. And this one, the summa, will be if in the case that we have, will be the term that includes the connectivity part of the network. In this case, we don't have anything. So if you run this exercise, in the case that we have A equals 0, you can see one plot like this. That is here we have the simulation time, here we have the signal, and here you can see that the signal that we have contains a sum of the noisy signal and also some oscillators. So here we have the phase transition. In the case that we set the local bifurcation to 1, to be like the positive one, like this, the positive regime of this Hopf oscillator, you can see that the dynamics that we have, or the dynamics that this oscillator explains, are sustained oscillations, as you can see here. And the frequency will depend on the omega that we have set. Finally, if we set the bifurcation parameter to -1, so here the important value is that we have or negative or positive or 0. And if you try with other values, you can see that the effect of the oscillators of the oscillation could be more pronounced. In this case, with negative value, you can see that what we obtain are noisy oscillations. So what we can see here is merely noise. So from this exercise, what we can learn, or what we can see, is that if we change the local bifurcation parameter, this A, we can obtain different dynamics, and the oscillator is describing different dynamics. So
okay, so basically this is a summary of the results that we got for the 3 situations. So for sustained oscillations with positive A, noisy oscillations for negative A, and then at the exactly at the bifurcation point where we have the phase transition, we have A0. So also now here we can compare the three results, and you should also have a look at the different scales. So for A1 we have oscillations with this amplitude around 1. For A0 we have this mix, as Anne was describing, oscillations with noise, but these oscillations are of lower magnitude, and with A negative we have purely noise. Now you can try in the scripts in exercise 1, you can try using smaller A's, and if you use smaller A's, you will see that for instance here that it takes some time for this noise at the beginning to reach the full amplitude. If you use smaller A's, you will see that it takes longer time for the system to reach the oscillatory regime, and also that this oscillatory regime is going to have lower amplitude. So now we move to part 2. So in this first part, we just skipped the global coupling between the coupling between the different nodes. Now we incorporate this part here, and of course we can fix different values of A. Typically we fix A equals 0. This is what is typically done initially, based on different research papers that suggest that that different brain regions are working at the onset of the bifurcation of this parameter. But now we incorporate here the input from other regions, and what we're going to do in this second part is to simulate couple dynamics in a network of oscillators. So because we are working just with an example, we give you a network of 10 nodes which are linked with the following structural connectivity. So here we have 10 nodes. 0 means that there is no connection, 1 that they are fully connected. So there is one module here of nodes fully connected, another module here, and then we have node 4, which is a hub, which is interconnecting the two modules. So now we're going to be interested in understanding what happens when we change G. So C is fixed, and we have the local variables, the local dynamics also fixed, but we also have, apart from the local dynamics, we have an input from other nodes. So how does G affect the local activity? And G controls for the global connectivity of the fibers. So basically, we have the same structural connectivity, but as we increase G, it's like we are increasing the conductivity of fibers. So we allow for more electrical current to arrive to different regions. So now the effect of global coupling basically can be summarized like this. You can imagine the couplings becoming stronger, the structural connectivity having a stronger effect on the functional connectivity. Now, the exercise that we will do, exercise 2, we use the network that I just showed you. So we have 10 nodes which are interconnected in these two modules with one hub in the middle. We will be working with A equals 0, which is based, as we said on previous studies, which suggest that the best fit to empirical data arises at the brink, at the edge of a Hopf bifurcation, and we use A0 except for the hub. And we set the hub at A equals 1, so that we have sustained oscillations at least in one node that can spread to the rest of the network. Now we will simulate the network dynamics for different situations. So for G positive, if G is 0, we are in the case in which there is no coupling, which is the one that we just described. Now we will take different values of G positive. For instance, G 0.5. This is an example that we will just show you, and then we will also show the results for different G's, for instance 0.2, and you can play with other values. So I give floor again to Anne.
Okay, so here we have the second exercise. So this is the same script that you have in the virtual machine. As Manel said, first of all, we are going to define the network. So this network will be very simple. It consists of 10 nodes, and if you run only this part of the code, you can see that we have indeed the matrix that Manel explained with 2 modules and 1 hub. Okay, so if you want later, you can also play with this structural connectivity, and you can also define different, for example, different models or different a network with different complexity. This is the one that we are going to use here. So for the first case, as Manel said, first of all, we are going to, well, we can do first without coupling. So saying, okay, we are going to have different oscillators, and each oscillator will work in the regime that it wants. So if we do like this, we set the omega as we did before with an angular velocity that is fixed. And here we defined the values of the bifurcation parameters. So in this case, for example, for all the values or for all the nodes, we can set to 0, and this will be the value of the bifurcation parameter in the hub. Okay, this will be the hub because we have defined the node 4 as the hub, and the G will be the global coupling. Here in this part of the script, we are going to define again the basic parameters of the model, such as the time or also the multiplication between the global coupling and the structural connectivity. These are model parameters. Then again, we train the model. So here we have the equation. In this case, this part that before we didn't have it, or we have it but set to 0, here we are going to have it and will depend on the level, on the value of the G, that is the global coupling. So in case that we run like this, so in this case we have the G equals 0 and all the A's are equal 0, only the hub, the dynamics of the hub, okay, here, are different. So you can see here the signals, okay, or the dynamics that we can simulate. You can see that the node 4, that is the one that we have the hub, is the one that show the oscillations, because we have set the A, the local bifurcation parameters, to 1. And the rest, they show different dynamics because they are not coupled. The G is equal 0. This can be also shown in the functional connectivity, which we have it here, where you can see that there are plenty of, well, there are several correlations that they show very high levels of randomness. If we use other value of the global coupling, for example, 0.2, as I said, as we recommend in the exercise or in the PDF, what we are going to see here would be different dynamics, because we will have the coupling, so we will have some interactions between the nodes. So they are going to be interconnected. In this case, again, we have the global, we have the node 4, that is the hub, will show oscillations, and the rest, because of the influence of the hubs, they are going to change the dynamics. As you can see here, that before we saw random dynamics, or each of the nodes had different signals. Here you can see that the signals are more similar. They start having some oscillator because of this coupling and because of the influence of the hub. And we can also see it here, in the functional connectivity, where you can see, as you can see here, that, for example, this second module, it synchronized, so it shows very high correlations between the nodes because of this coupling that we have increased. Here you can use different values, or different values. You can change both the coupling and also the local dynamics. In the case that we have also, for example, the hub that is in the phase transition, or and if we use also a global coupling, so it still are connected, we can see that also we found different dynamics. In this case, what we found, is that almost all so noisy oscillate, well, also noisy oscillation, but comparing with the functional connectivity that we had before, you can see here that there are some couplings, so there are some influence in the modules, in the nodes that are inside or within this module. And you can see here in the functional connectivity that here the levels of correlation are higher than the ones that we see, than the ones that I saw before with the G equals 0 to all the cases for all the global coupling. So as you can see here, if we play with this value, so you can see here in the 37 line and the 40 to 42. So these are going to give us, or to allow us to simulate different complexity of the network and different networks that that have different dynamics. And yeah, we proposed in the PDF, we have proposed different different values that also allow us to observe different network complexity, as I can show you here as solution of the second exercise. Here, as I said, we have the G equals 0, so this is the one that I saw before. And if we compare with the G, so with a global coupling that is with an increased value, you can see that here we have almost all correlated. Also, you can see it in the signals. And for the case that we have the G equal 0.2, we saw that there is some effect because there are some network effect here in the modules, but still not, is not, well, it's an intermediate cases in between the two. Also, well, maybe, I don't know if you are trying, I don't know if we can have some feedback in the chat, well, but yeah, it can be interesting if you try to use different values of the global coupling, because this will be also very interesting in order to understand the next step, the next exercise. And in the case, for example, in an extreme case where we have a very high global coupling, what you can see also is that we have a very extreme case where we have almost well, very clear that we have the two modules that they work in compact. These two, the nodes of the two modules work in compact, but they don't talk between each other, or they talk less. As you can see here, that the correlation here, the level of correlation is lower compared to the ones that we see inside of the modules. Yeah. So, well, it's interesting if you, I don't know if you are trying in your virtual machine, but yeah, this could be interesting.
Okay, so this is exercise 2. Now we go to part 3. So what we have seen so far is just a model, and we have been playing with different parameters. We did different simulations. We saw how the different, basically two parameters, which is the bifurcation parameter and the global coupling, affect the results. Now the question is, what do we do with this if we want to understand something regarding real data? So for part 3, we are going to work with fitting and modeling real resting state data. We have resting state fMRI recordings from one subject in this case. So in some cases we work with more subjects, but just to give you a sense of what we are doing, we have resting state recordings from one subject. So now we have these resting state fMRI recordings, we have our model, and the question or the main objective here would be to get the network model reproduce some dynamical properties of the real data. And we have basically two parameters that we can tune. So we have a bifurcation parameter and we have the global coupling. So there are, well, G is just one parameter, we have A, so one for each node. So we can play with all these parameters, we can change all of them and try to see if the model can reproduce some dynamical property. Now, when we do this, when we try to make the model reproduce real properties, what we are doing is what we call fitting. When we do this fitting, we can have different objective functions. For instance, metastability. In Gustavo Deco's lecture, we have seen different of these functions. We can have a metastability, the functional connectivity. So, for instance, we can try and look for the grand average functional connectivity, and we might want the model to reproduce this. Or another function that is commonly used is the functional connectivity dynamics. So this is the one that we are going to use to fit our model in this part of the tutorial. Now, we have again the equation here, which is just describing the model. And we are looking for the G. So here we would have a model. The subject that we have has 83 brain regions. So we have a model with 83 nodes. We plug in the structural connectivity that we get from DTI. We extract the omegas from the original, from the empirical data, and then we want to find the G that minimizes the distance between the empirical and simulated functional connectivity dynamics. So we are fitting, we are optimizing the fitting of the model based on tuning this G parameter. So this is what we typically have. We have the empirical functional connectivity dynamics. We have simulated functional connectivity dynamics for different values of G. Now we use the Kolmogorov-Smirnov distance for each of these different FCD matrices, and we compare the two. So basically what we are plotting here is the KS distance for each G value. And what we see is that when we have a G which is very small, so all nodes are completely isolated from each other, the distance is very large. So the empirical and the simulated FCDs are very different. Now, at some point, there is a range of G values where the simulated FCD resembles the empirical FCD. And then this property is lost again. So this is how we find the G that we were looking for. This is the G that would make our model reproduce this dynamical property, which is the functional connectivity dynamics. So in this exercise, what we are going to play with is with real data. So you can open the script named exercise 3. We have the structural connectivity and the bold time series of one subject that are loaded in the MATLAB file. Then we fix all model parameters and run the modeling part of the script. And here we compute the functional connectivity, the power spectrum. So we first compute some properties that we will need to later simulate data, simulate the empirical signals. Then we are going to try with different values of G and compute the KS distance for each of these G values. I think in particular, we try with 4 values of G, and then we will do this plot. So basically this plot that I showed here. And now I give floor to Anne.
Okay, so this is the script for the exercise 3. Well, here, first of all, we are going to load, as Manel said, the structural connectivity and the bold time series. So here, first of all, I would like to show you, the structural connectivity. So you have an idea of what we have. So we have it here. So this is the structural connectivity that we have for this subject. Okay. So as you can see, we have all kind of values from 0 to 1, and here we have the interconnections between the nodes given by the structural connectivity. Okay. And on the other hand, we have also the time series that are given like this in the sorry. Okay, these are the time series. So these are the data that we are going to use from the subject in order to feed and in order to set all the model parameters of the model. Okay, so here we have again the first part where we are going to set the basic parameters that will be depending on the signals and on the structural connectors that we have. Okay, so in this case, here we have the time points, and as Manel said, we are going to use 4 values of the global coupling. Okay, these values now are fixed because, well, we know which ones are the ones that have our representative values or representative results of what we want to show. But also you can use, for example, here we have commented, but if you use all these range, you are going to have a higher resolution and also more informative description of the results. Okay, but here, because of the limitation of time, we are going to use only these 4 values of the global coupling. In this case, we also have 1 subject. You can have more. And there is here a normalization of the structural connectome also that is done in order to prevent the full synchronization of the network. Okay, so here we have a maximum value of the structural connectome set to 0.42. That is an arbitrary decision in order to to not to prevent this oscillation of the network. And furthermore, here we are going to set also the value of the TR of the recordings. Okay. Here we have again some values here. Here in this script, what I present is also an homogeneous model. So in this case, we are not going to We are not going to optimize the values of the local bifurcation parameters. We are going to set to 0, as Gustavo Deco has explained this morning in his presentation, that if we do it in this range, we have the optimal fitting in the case of the local bifurcation parameter. So here later I will explain an extra exercise to consider the local bifurcation parameters. But in this case, we are going to consider only the values of the G's. Another important point of this script is that we use the properties of the power spectrum. So in this case, we are going to use a low band pass filter that goes from 0.04 to 0.07 to filter the signals, the volt signal that we have. And this filter is defined in this part of the script, as you can see here. That also depends in the TR that you have. And after filtering the signals, as you can see here, well, we filter the signals in this narrow band, and we can extract the power spectrum. Okay, here in this line, we extract the power spectrum of the band pass filter signals. And we also we are going to use the peak of this power spectrum to define the omega, or the frequency, the intrinsic frequency of each node. Okay, so in the previous exercise we have set this value of the omega, or the power of the intrinsic frequency, but in this case we are going to extract this value from the data. Okay. And then what we can do also is to extract the phases of the signals based on the Hilbert transformation, because here the functional connectivity dynamics that we are going to use, or the functional connectivity dynamics, is based on the phases instead of from the signal directly, as Gustavo has explained in the morning. So once that we have all the empirical measures as the functional connectivity dynamics, that is the measure, or the metric that we are going to compare between the empirical and the simulated data. So here we have the empirical, and we have also the information of the power spectrum. We can go directly to the simulation and the simulation first of all. So we have the different value of the G's, as I said. Here in this case we have 4. And we are going to calculate the functional connectivity dynamics of the simulated signals using these values of the G. As I said before, here we have the values of A, and in this case, these values of A's, or the bifurcation parameter, are going to set to 0. So here, this part, we have the homogeneous model, okay? What we call the simulation of the homogeneous model. So the big part of the A's are going to set based on this previous A, and here we have first an initialized part for training the model. So we are going to initialize the model. So we are like warming the model. So the signals that we obtain have already stabilized, and the dynamics that we see are the ones that we want to simulate. So this is the first part, the training of the model, so the warming of the time series. And here in this second part, so from the line 172, we are going to have the real simulation of the modeling. So this depends on the data that you have, on the subjects that you have, and also in the TR. And here you can see that here we have the same equation that I have already explained in the exercise 1 and in the exercise 2. So this is the equation that will give us the simulation of the iteration of the model. And well, as I said before, this equation depends on this summa variable that contains the effect of the global coupling, and also the structural connector, but especially the global coupling. So this is the one that will change in the different iterations. once we finish with this simulation of the signals, we can, we have already the time series, the simulated time series, that will be this zeta variables. So this zeta vector will contain the simulated time series. And from here, we can start, as we have done in the exercise 2, for example, computing the functional connectivity, or we can also compute the phases and the functional connectivity dynamics. So in this last part, where we have brought computing the fitting, here we are going to calculate the functional connectivity dynamics based on this pattern cons function. Okay. Here, what we do is we compute the cosine similarity between the functional connectivity calculated with the phases in different time windows. Okay, but the idea is the same of the functional connectivity dynamics. In this case, we have also included in the virtual machine this vector or this file, which contains the functional connectivity dynamics that has been already calculated, because this is the part that needs more time. So well, if you want, you can uncomment this part and you will obtain the same results. Okay. So finally, here we have the case test, which is the, as Manel explained before, the Kolmogorov-Smirnov distance between the both functional connectivity dynamics. So here, here the empirical one, and here the simulated one. So if we run this script, that it would take a while, because we have this the simulation for the different global couplings. As I said, we have 4. So in this case, we have 0.04, that is very low global coupling. Then we have 0.2, and then we have 0.5, and also an extreme cases where we have 0.8. So from here, you can, well, in the previous exercise, these are the more or less the global couplings that we have used. So in order to have the same, more or less the same range of values of the global coupling. So as you can see here, it takes a little bit to simulate the model. Mainly the most part of this time is for performing the calculation of the functional connectivity dynamics more than for the model. Because in this case, it's an homogeneous model, so we are not fixing also the local bifurcation parameters. And in the final part of this script, we have included also the figure of here, the representation of the plotting of the global couplings and of the and the values of the Kolmogorov-Smirnov distance. Okay. So from here, okay. Oh, sorry. This is the next exercise. Okay. Okay. So we obtain something like this. This fitting changes for every time that we run the model, because we have also some effects, some random effects, for example, the noise, and well, mainly the noise. So there could be some changes in the fitting. Okay, so maybe if you do in the virtual machine, or if you do at your home or whatever, maybe the results are a little bit different. Indeed, the results, if you compare with the ones that we saw in the PDF, there are some little changes. But you can see here that we have for the 4 points, so we have for the 0.02, for the 0.2, no, 0.04, 0.02, and 0.5, and then for the 0.8. Okay, so you can see different values, mainly here. I don't know. Okay, yeah. So as Manel explained it, this the fitting or the Kolmogorov-Smirnov distance between the distribution of the functional connectivity dynamic changes with the different global couplings. You can see here that that the difference is very high for a global coupling that is very small. That here for 0.2 we have the minimal distance between the, well, we have a very low distance between the distribution of the functional connectivity dynamics of the empirical and the simulated one, and here we have also higher values. So this means that in this case here we have the optimal global coupling or the optimal fitting between the simulated and empirical data. Furthermore, in the final part of the script here, we have also included a file where that is called KeySP, where we have an example for all the values for all the resolution between 0 and 1, considering a resolution of 0.01 of one subject. And if you also plot here this if you run this part of the script, you will have some kind of plot like this, where you can see that here we still have some noise, because, well, this depends on also in the simulation, and it depends on the different values. So the best thing is to run the model many times, so this way we can have a good approximation of the fitting. But you can see here that for this range, around 0.2 or around between 0.2 and 0.3, we have the minimal values of the distance. So this way we can extract which is the optimal coupling for this individual, doing many more trials. And so, as I said, here we have the results for the third exercise for this case. And also from this presentation, from this tutorial, we can conclude that, well, this whole brain modeling can allow us to investigate the interplay between the dynamics and the structural features, as we have shown with the different exercise. That in the first exercise, for example, we only use the dynamical aspect of the Hopf oscillators. In the second one, we included the structural features, and in the third one, we interplay both using also a real system as one subject or one resting still subject. And we have also shown that, well, this Hopf oscillator can be applied to indeed simulate and also explain the mechanism that is underlying the nonlinear brain dynamics. We want also to include some additional material. So, for example, some examples of this model can be found in these three parent aspects. For example, there has been a paper that showed that this model can be used in order to also study the stability of the nodes and also the heterogeneity of the brain dynamics. In this case, you have also the link to the paper and also to the scripts in the PDF. And here there are some, well, also in the PDF, we suggest some extra exercise where you can also play with the heterogeneity of the local nodes. Then also this Hopf oscillator-based method has been used for estimating the effective connectivity. So here also we propose some papers. And finally, there are very recent approaches to use this model for studying the turbulent like dynamics. And then, as I said, some bonus exercise on the PDF. So this is our presentation and our tutorial. We hope you enjoy.